Welcome to the Explainer. You've definitely heard the term blockchain thrown around, but what is it really? Today, we're going to pull back the curtain on the technology behind the buzz and figure out why some people are calling it the unbreakable digital notebook.
But let's start with a really basic question for our digital world. I mean, think about it. When you can copy and paste pretty much anything with a single click, how can you ever be sure that what you're looking at, a file, a transaction, any piece of data, is the real deal? How do you know it hasn't been tampered with?
For a lot of people, the answer is blockchain. Now, IBM has a pretty good simple definition. It's a shared, unchangeable digital ledger. So don't think of it like a Word document that anyone can go in and edit. It's more like a digital stone tablet that everyone in a network gets a copy of. And once something's carved into it, it is there for good. That's how you get a single source of truth everyone can agree on.
Okay, so what makes this digital notebook so special? What does that fancy word, immutable, really mean here? Well, it all comes down to its core structure, how it's built, block by block. Here's how it works. You take a whole bunch of transactions and you bundle them together into something called a block. Then, and this is the important part, that new block gets securely linked to the one that came before it using some really clever math or cryptography. You keep doing this and you get a chain. The result, a permanent chronological record of everything that's happened. So, how exactly are these blocks linked so securely? Well, it all comes down to the cryptographic glue that holds the whole thing together. And the magic ingredient in that glue is something called a hash function. According to Geeks for Geeks, a great way to think about a hash function is like a unique digital fingerprint generator. You can feed it anything, a single word, an entire novel, and it will spit out a totally unique, fixed-size ID for that data. That's its hash. Now, for this digital fingerprint to actually be secure, it needs to have a few key features. It's got to be deterministic, which just means the same input will always give you the exact same fingerprint. It also has to be basically impossible to reverse engineer, but the property that is just so visually powerful is what's known as the avalanche effect. And this slide just illustrates it perfectly. Look at this. The first input, the explainer, is great. Gives you a specific hash. But now watch what happens when we add just a single period to the end. The output hash isn't just a little different, it is completely, wildly different. That right there is the avalanche effect. So this brings us right to the heart of blockchain security. Every single block contains the unique hash, that digital fingerprint, of the block right before it. So if some bad actor tried to go back and alter even one tiny detail in a past block, its hash would completely change. And that would break the link to the next block, which would break the link to the block after that. It sets off a chain reaction that the whole network would see immediately. It is an absolutely brilliant digital tripwire. But hang on. If there's no central authority, no bank, no government, nobody in charge, then who gets to add the next block to the chain? How does everyone agree on what the official record is? This is where this fascinating and kind of wild process called mining comes into play. The technical name for this is proof of work. Wikipedia explains it as a system where participants, who we call miners, have to prove that they've spent a whole lot of computational energy. It really is like a global digital race to solve an incredibly complex math puzzle. And what's really interesting is that this idea isn't even new. It actually started way back in the 90s as a clever way to fight email spam by making it really expensive for spammers to send out millions of emails. But it was Satoshi Nakamoto who brilliantly adapted that idea in 2009 to be the security backbone of Bitcoin, and that's what launched it into the mainstream. And right here is the real genius of proof of work. It's all about asymmetry. Solving the puzzle to get to add the next block is ridiculously hard. It takes an immense amount of computing power. But once a miner finds that solution, it's incredibly easy and fast for everyone else on the network to check their work and say, yep, that's correct. Hard to do, easy to verify. Okay, so we've got the basics down, right? We have linked blocks, we've got these cryptographic hashes, and we've got this huge race to add the next one. But why does any of this matter for things that aren't cryptocurrency? Let's zoom out and look at the big picture. So much of the potential here is unlocked by something called smart contracts. Now, don't let the name scare you. They're basically just little computer programs that live on the blockchain. They're programmed with simple rules like, if this thing happens, then automatically do that thing. And because they live on the blockchain, they just run exactly as programmed. No need for a middleman to enforce anything. It's this idea of programmability, this ability to bake the rules right into the ledger itself, that just blows the doors wide open for potential uses that go way, way beyond just sending digital money around.
And as this research shows, entire industries are exploring this right now. I mean, in supply chains, you could track a product from the farm to the store with absolute certainty. In healthcare, you could have secure patient records that you control. People are even designing e-voting systems where the results are completely transparent and impossible to mess with.
But okay, to give you the full story, we have to talk about the downsides. Because this technology, and especially that proof of work system we talked about, is not perfect. It comes with some really significant challenges and criticisms that you need to know about. The biggest one, the elephant in the room, is energy. That digital race to solve the puzzle for proof of work takes an astronomical amount of electricity. I mean, to put it into perspective, back in 2018, the Bitcoin network, just by itself, was estimated to be using as much electricity as the entire country of Switzerland. Let that sink in for a minute. And while it's incredibly secure, it's not invincible. There are theoretical attacks, like a 51% attack, where if someone could get control of over half the network's computing power, they could actually manipulate the blockchain. Plus, there are some big economic questions about whether the incentives for miners will be strong enough to keep the network secure decades from now, as the rewards for mining get smaller and smaller.
So, what's the big takeaway here? Blockchain offers a genuinely new and really powerful way to create trust in a digital world. But the story isn't over. The big question now is whether we can build on this amazing foundation and innovate past its most costly flaws, like that huge energy cost, to build a more efficient and sustainable future for it. And that right there is the question that the brightest minds in this field are trying to answer as we speak.